This is Marc Strassman, reporter with the Online Broadcasting Services Internet channel. We're in Boulter Hall on the UCLA campus, and we're about to talk to former chairman of the Computer Science Department, now a professor there, Dr. Leonard Kleinrock. Welcome to Online Broadcasting Services Internet channel.
Pleasure to be here, Marc.
The last time I did an interview with you, which was 1997, I was using a camera that was 10 times bigger than this one, cost twice as much, and took pictures of far lower quality. How much of this is a tribute to Moore's Law, and how does it track the increase in power of the Internet in the 9 years since we've last spoken?
Well, we've seen Moore's Law everywhere in our technology domain, and reduced size of cameras, increased performance, reduced cost is clearly one of the manifestations. The Internet, on the other hand, has been growing exponentially as well, but bandwidth has been growing more quickly than that in terms of the cost and the available bandwidth. So we're in the midst of a wealth, an embarrassment of riches in technology and in use of technology. It's a fast-moving world we find ourselves in today.
And a lot of it, of course, depends on the packet switching nature of the Internet, and that's what I wanted to talk about first, which was your contribution to that, and even further behind that, why you decided a while ago to go into electrical engineering. What was your motivation? Did you have a vision, or you were looking for work?
Well, you've asked two questions. Why I went into electrical engineering goes back to when I was a 6-year-old boy reading a comic book. And in the middle of the comic book, I found a description of how to build a crystal radio. And so I did build that. I managed to collect the parts. They were all free, except for a variable capacitor, which I had to buy down a Canal Street in Manhattan. Put it together, no power, no batteries, and music came out of the earphones I had stolen from the telephone company. I was amazed, and I wanted to know how this worked and where this magic came from. And so I started studying electronics and building radios from then on. The thing that led me to the Internet technology, though, is much further along in my career. I was a graduate student at MIT, and I was surrounded by computers, and none of them could talk to each other. And I realized that it wouldn't be too long before they needed to communicate for a variety of reasons. And I also recognized there was no suitable technology which will allow that to happen efficiently. The network at that time, of course, was the telephone network. And the telephone network has a fundamental problem. The problem is that when I speak to you over a telephone link, the resources connecting us together are completely dedicated to our conversation. At least in those days it was. So if I stop to have a cup of coffee or step outside for a moment while holding a telephone connection open, that wasted bandwidth would still be wasted and allocated to us. That's not an unreasonable thing to do when you're talking about speech, because in speech you're silent about 1/3 of the time. In data communications you're silent 99.999, as many nines as you like, percent of the time. And so we couldn't afford to do it so inefficiently. So the key was to find a way to be able to reuse those resources for other things while our communications was pausing, as it does so frequently in the bursty data communications field. And basically I decided the trick was to find a resource sharing technology. One manifestation of resource sharing is packet switching. There are many others, by the way. Any one would have worked as long as you get the efficient use of resources when people need to use them, and not assign them to people when they're not using them.
Now, I'm sure it may be apocryphal that Isaac Newton was sitting under a tree and saw an apple fall, and he said, "Aha, gravity." Was there an exact moment when you developed packet switching and saw that as a way to solve this problem?
Well, if anything was like an aha, it was a recognition that there already existed time-sharing systems which did exactly that. In time-sharing systems, which were already being developed at the time, one could share the resources of a computer among many people. While I was using it, no one else could. When I paused to debug a program, other people could. So the system would automatically shift to whoever needed it. This is exactly what we needed for networking and data communications.
So what you're saying essentially is that the paradigm of time sharing, where the CPU allocates its attention, so to speak, to whoever is inputting to it, you expanded to a network so that it would essentially have that same kind of time-sharing structure or paradigm within an entire network.
That's exactly right. The idea of demand access. When you need it, you get it. When you don't need it, somebody else can use it. Timesharing is a perfect example of that. Packet switching was one manifestation of that in the networking world. There are many other manifestations of resource sharing in networking. For example, polling, message switching, any kind of demand access will give you that characteristic, and that's what works.
All right. Now, you developed these ideas while you were a graduate student at MIT and got your PhD in 1963. Did you do your thesis on packet switching?
Exactly. I was in the EE department at MIT, and I was surrounded by people doing work on information theory. Shannon was there at MIT in the EE department at the same time. And I noticed all my classmates were working on that problem of coding theory, source coding, error correction codes, etc. And I said to myself, Shannon's done most of the good work here. What's left are hard problems, probably of relatively small consequence, and I didn't want to do that. So I looked around for some other field, and I noticed this issue about computers talking to each other. And so yes, I did this work as a graduate student and published my dissertation in December of '62.
Okay, now, it wasn't until 1969 when the first ARPANET message was sent from your node here at UCLA to SRI in Menlo Park. What happened in those 6 years? Would 6 years go by now between the development of this kind of idea and its implementation in hardware and a network? Or why did it take 6 years for the theory to become practice?
Well, the reason it took so long was the following. There was a single network at the time, as I mentioned, the telephone network. ATT was dominant. And all through those years you're discussing, those 6 or 7 years, I would be beating on them, as would others in my field, saying, please give us good data communications. I remember being on panels, the major conferences in the field at the time. And I'd be saying, please give us good data communications. And ATT would say, what are you talking about? The United States is a copper mine. It's full of telephone wires. Use that. And my answer would be, no, you don't understand. It takes you 25 seconds to dial up a call. You charge me a minimum of 3 minutes on a call, and all I want to send is 100 milliseconds of data. And their response was, little boy, go away. And the reason they said that is because all the money was in voice communications. There was no revenue visible to them for data communication. So it was largely a lack of economic motivation on their part and a lack of vision to see the future would be data. And both those failures caused a delay and caused serious consequences to the telephone companies as we knew them at the time.
What finally happened in 1969 that made it possible for you to implement your theoretical views from 1963?
Well, it actually goes back to 1957,
okay,
when Sputnik was launched.
Right.
When Sputnik was launched, the United States was caught with its pants down. And so President Eisenhower decided to never let that happen again and created the Advanced Research Projects Agency. And one of the things they did was fund advanced research in computer science. And they had been doing this all these many years. By the time the mid-60s came around, they had basically funded many researchers across the United States to do excellent and advanced computer research. And each one of them had developed expertise around the computers that they had been receiving in a special way. For example, University of Utah had excellent graphics communications and capability. UCLA, simulation. SRI, database. University of Illinois, high-performance machines. And so every time ARPA, the Advanced Research Project Agency, came to a new researcher and said, we'd like you to do research for us, the researcher would say, you want me to do research? Fine, buy me a big computer. ARPA said, fine, you know how to do that. But not only that, the researcher would say, I want all the capabilities everybody else has. I want the graphics, the simulation, the database, the high performance. And ARPA said, we can't afford to do that. And so they recognized if they put all these resources in a network, then if someone wanted to do graphics, they would go through the network and log on to Utah. Simulation, log on to UCLA. And so the concept was born in the mid-60s, in fact in 1966 and 1967, when ARPA said we want a network. And so the concept of the ARP network was launched at that point and implemented in 1969.
So in fact, the problem that you had identified early in the 60s at MIT about the need for computers to talk to each other had now reached, instantiated itself in a project that had money behind it and a lot of desire to solve it, and that provided the breakthrough that allowed you to create the ARPANET.
That's exactly right. The key statement there was money behind it. The Defense Department had the money, they had the will, and they had the vision to make a high risk, high payoff bet that this technology would be useful.
And in fact, it would be useful in terms of national security, which was the highest priority for ARPANET.
Well,
Or was
yes
it?
and no. That
All
was
right.
not the highest priority for ARPANET.
All right.
The highest priority was just what I said, to share resources. They couldn't afford to give everybody everything. So they wanted to do the same thing that drove me in my technology to do resource sharing at the communications level. They wanted to do resource sharing at the high level of machines, of applications, of software, of particular specialized hardware.
Okay, now talk a little bit about the particulars of how that first ARPANET message was sent from UCLA to SRI in Menlo Park.
Okay, well, as you suggested, UCLA became the first node on this ARPANET. And the reason is because we had the expertise here from my earlier research. So in September '69, the first switch arrived at UCLA, a thing called an Interface Message Processor, otherwise known as an IMP, fondly known as an IMP. The second IMP was located at Stanford Research Institute. And in each of these two locations, we connected a host computer. We had a time-sharing system here running on a Sigma 7, and they had a time-sharing system running on a PDP machine. And so by the time they got their machine, in late October, we decided to send a message from UCLA to SRI.
Now these IMPs are essentially Ur modems. Is that a way to think of them?
Well, they are master modems.
Right.
They're basically devices that offload all of the communications load from the host
Right.
onto the network.
Right.
And the network was this network of IMPs connected together by high-speed lines.
Okay. Was this paid for by ARPA? And who was up there at SRI as your counterpart?
Well, it was all paid for by ARPA. They funded the machines, they funded the switches, they funded the links, they funded the network, they funded the company that put all this together, both Beranek and Newman. And basically up there we had Doug Engelbart. He was in charge of a lot of the research going on up there.
Okay.
And so the first message, all we wanted to do, you know, you think it might be a good message like, what hath God wrought?
Right.
Or come here, Watson, I need you.
That's
or
right.
a giant leap for mankind.
That's
No
right.
way. Those guys were smart.
Right.
They understood about public relations. They had a good message. They had the press and the media there. They had cameras if the cameras were available, voice recorders, someone making a record of this. We had none of that. There were two of us, myself and one of my programmers, Charlie Klein. We decided we needed to log in to the machine up at SRI from the machine at UCLA, from the host machine. Now, in order to log in, we have to type LOG, and the SRI time-sharing system recognizes we're trying to log in, and it will type back the IN for us. So, I got Charlie with his earphone connected to a telephone set, talking to the programmer up there. And he typed the L, and he said, "You get the L?" And the response was, "Got the L." Type the O, get the O, got the O. Type the G, get the G, crash. The SRI machine crashed.
After L and O.
After L and O. Basically, it had a memory leak.
Right.
And it wasn't the IMP, it
Right.
wasn't the network, it wasn't our host, it was the SRI host.
Memory overflow there with two characters.
Memory overflow. Well, there's a lot going on in the background, as you
Right,
can
okay.
imagine. So the first message ever on the internet was low,
Right.
as in lo and behold.
You're right. So that's good. All right. So now the ARPANET's been set up. It became the internet, and now we're going to rush ahead to the present, having established that. And we have about 20 minutes left of recording time here. And I'd like to talk about some current issues in the internet.
Sure.
When I talked to you in 1997, you mentioned in particular that you were using the internet to find out about getting a digital PBX. Did you get that PBX?
Yes, I did.
And
Well, actually, no. When we talked, I was getting an analog PBX.
Oh, okay.
And I was told not to get the digital
Right.
by a collection of people anonymously out there on the internet, and it was a good decision.
all right, good. Tell us what you use the internet for today in 2006.
I use it for all the same things everybody else does. Information, interaction, keeping up with what's going on in my field, communication, and accessing all the people I want to access in an interactive and dynamic fashion.
Okay, now everyone should be able to do that. There's still such a thing as the digital divide. What is it, and how do you see that right now? And do you think it's disappearing? Do you think the government needs to do more? Do schools need to do more? What's important about reducing or eliminating the digital divide, and where do you think things stand in that regard now?
Well, the digital divide occurs not only with relation to developed countries and developing countries. It occurs within developed countries as well. When I think some of those young people who live below the poverty line, whose main concern is poverty, hunger, drugs, crime, abuse, shelter, they can't afford to think about something as sophisticated as the internet or access to a computer. So we have that same problem in our own country today. What to do about it? Well, the internet in some sense is a leveling mechanism. If we can get an inexpensive machine and inexpensive access out to many more people, hundreds of millions more people than we have today, we will allow them to participate in this grand development. I would call it an experiment, but it's beyond that today, called the internet, whereby they can access the world's knowledge, interact with each other, create things, put them on the net, have other people share them and share other people's creative works. This is one of the things which can help, but it also increases the divide if you can't provide that kind of capability to people.
Now, Thomas Friedman has written "The World is Flat." He addresses this issue and says the internet is a powerful flattener of the world, making collaboration and forms of competition easier. But there's still an unflat world where people are not logged in. What do you see as the role of the internet in spreading the flattening of the world, and what kind of impact do you think that's had so far, and what impact do you expect it to have in the near and medium-term future?
Well, there's no question that it's a flattening mechanism if you can give the essentials, the minimum necessary to get on the internet. In some sense, just as dial tone should be free, telephony dial tone should be free to everyone, so should internet dial tone. Anyone should be able to get access to the internet to do at least a minimum set of functions such as email and small search. If you want more sophisticated technology, okay, perhaps you have to put an economic cost in there. But to be able to provide access to everyone, or nearly everyone, in the world is, I think, the goal we're trying to achieve. It's not free. Governments can provide the mechanism to make that happen. The world, in fact, must do that, because without doing that, the digital divide, as you said, will create social, political, and economic divide, and therein lies the problems that lead to terrorism, wars, famine, droughts, etc.
Now, the data rate of the first ARPANET communication was apparently sort of a bit or so per minute overall. Broadband is now spreading more widely. Is what passes for broadband in the United States what passes for broadband in South Korea? And what is broadband? What's adequate broadband? What's enough broadband in your view?
Well, the actual speed of the original ARPANET was 50 kilobits per second. In those days, that was a blazing speed. 36 years since then, we've come up with some of these handheld devices which give access to the internet. Guess what speed this thing connects at typically? 50 kilobits per second.
Well, that's not much of an improvement.
Not much of an improvement, but it is a wireless technology. Broadband is almost anything you define it to be. Something on the order of a few hundred kilobits per second and on up, so that people can get a sense of interaction on the internet and not very slow motion text or extremely slow motion image and video.
Compare the fields of computer science and information technology.
Computer science is a very broad field, but people tend to compartmentalize it and think it deals with simply algorithms or software or building of computers. In fact, it's much more than that. It's computer systems, it's information systems, it's high technology systems as well. I mean, how would you classify the internet as a technology? It certainly is not studying algorithms by themselves. It's studying protocols, it's studying impact across social structures, it's studying access to information. So computer science clearly can be included in the definition of information technology and should be. And it's I think foolish to try to separate those two.
Okay, two other things about that it may be foolish to separate is the academic world, where you're primarily situated, and the business world. What's been your own experience in going back and forth between business and academia, and what do you think are the proper roles of each and the proper synergistic cooperation of the two?
Well, one thing that is nice is there is a very strong relationship these days between academia, government, and industry. There's a kind of cooperative effort. However, academia, with the proper support, is one of the few institutions that can take a long-range look ahead. And when I said the proper support, I'm talking about funding, which can come from the government, for example. Taking a long-range look, a 5, 10, 15, 20-year horizon. Industry cannot, and usually does not, afford to do that. They're looking at 1-year horizons, 2, 3 years. And so the kinds of technologies that come out, the kinds of breakthroughs we see are very different in those two worlds.
Share a little bit of your vision of that to the 15 to 20 year time frame, and talk about the major issues in computer science right now that are being addressed, and where you see the process taking computer science, IT, and the internet in 15 or 20 years.
Well, some of the issues we're looking at computer science now of the long-range type are a lot of the photonic work, a lot of the quantum theory and quantum computing, some of the biological computing, some of the pervasive computing. In this room that we're sitting in should be alive with technology. It should know I'm here. I should be able to talk to this room and get responses, intelligent responses. It should know my desires and present them to me. These are long-range thoughts that will take years and years to, first of all, understand, and secondly, to develop. The kinds of things that industry are interested in are the things that would lead to large industries and paradigm-shifting technologies. And those are some of the ones I mentioned earlier. But large systems lead to complexity. And if anything is perplexing the computer scientists today, as well as the technology implementers, the industry today, it's the fact that we're running into a complexity wall, and we don't know how to deal with it.
Is the complexity wall more of a challenge than the micron, the fact that the chip making is getting down to single atom level problems with bleed over and so on?
Well, I think the fact that we're reaching the limits of size is important, but that can be overcome in a number of ways, or dealt with in a number of ways, either through parallelism or through other technology we've not yet developed. I think the complexity issue, which comes from the fact that we have millions and billions of devices interacting, is one of the stumbling blocks we're going to have to deal with. And that's a very difficult one. It's something we do not understand today.
Talk a little bit more about what makes it a difficult problem, and what directions people are looking in for possible solutions.
Well, what makes it a difficult problem, it comes from one of two sources. Either a small number of very complex things like very heterogeneous systems, which themselves cannot be understood. On the other hand, it can be made up by vast numbers of very simple things whose complexity comes because of the interaction. Ways in which they interact, where properties emerge and we cannot in fact predict them. So the ways in which we're looking at these are asking ourselves, are there biological examples of how nature has dealt with complexity? Of course the answer is yes. As humans and designers, we used to believe that anything we built we could understand because we built it. And natural systems that were presented to us are much more complicated. That arrogance is no longer there. We cannot understand the systems we're building. They have emerging properties. They have behaviors we didn't build in just by their sheer size and interaction.
I was going to ask whether it's possible to model that complexity in computer systems, or whether the complexity itself makes it impossible to do that.
Well, the approaches that are being taken are
Right.
the following. One is to take a macroscopic approach. Whereas we may not be able to understand the behavior of the individual components, we may be able to predict the behavior of the system as a whole.
Is this like meteorology? Is this like predicting weather by understanding the behavior of millions of locations and temperatures and pressures? It is essentially an ecosystem of computing being created, and you're trying to understand it and control it in an analogous way?
The analogy perhaps is understanding how molecules behave, as you said.
Right.
Solving the three-body problem in physics is extremely difficult. We're talking about billion-body problems, and there is a theory that handles that. It's called thermodynamics, a macroscopic view, behavior of the system as a whole, even if you don't understand the way the components behave. And sometimes understanding the way the components behave will not allow you necessarily to understand the way the system behaves. We need a fresh approach. And there are a number of people looking at these fresh approaches.
If it's not classified, what kind of ideas are being floated out there?
Well, the ideas, as I say, coming from the biological sciences,
right,
the mathematical sciences, some of the thermodynamic, some of the high energy approaches. It's things like small world networks, emergent behavior. We're seeing chaos theory being used. We're seeing turbulence behavior. We're seeing stability and control theory coming in. All these fields need to be blended to get an understanding of this very complex thing we've created called high technology.
Is there an institute for this? Is there a central source of coordination here, or is it being distributed? Or are you and UCLA working on this problem and trying to become a center for the resolution of this issue?
It's being studied in many places. Santa Fe Institute is one example, but your other comment is correct. It's distributed across many, many institutions. And the reason is we don't yet have an approach. Well, everybody's probing this problem, trying to get a handle on it. We don't have the solution yet, and I doubt there's going to be a solution. It's going to be a collection of views that help us understand and therefore hopefully predict behavior.
And if this complexity issue is resolved, what would that then open up for further applications?
Well, certainly it allows us to build our systems in ways that perhaps we can predict behavior, but more importantly, to be able to anticipate failure modes. Every large system we have out there is subject to failure modes that we have not yet identified. The internet can crash, the electric power system can crash, the telephone system can crash, the World Wide Web can crash, and all of these things do crash for reasons that we did not anticipate. Once they crash, we understand how that particular crash occurred, and then on to the next one. It's just that the right, if you will, the wrong conditions have not been created to cause some of these failure modes to expose themselves. And if we understand more about the fragility of systems, hopefully we can predict when they will behave, when they will crash.
Ironically, or with prescience, this was the dramatic point around which 2001 rotated, when Hal predicted the failure of a component of his system and led to the exciting conclusion of that film. Talk about IPv6 and what it is and how important it is and when we can expect it.
Well, IPv6 is the next version of the Internet Protocol. It extends IPv4 in a number of ways. The most known way is it expands the address space dramatically. It also introduces some more aspects of security and addresses some quality of service issues. And it's been very slow in being adopted.
Why is that?
Well, for one thing, we have a legacy system, the old problem of an enormous legacy system, 1 billion users and nearly that number of attached devices. In fact, far more than that number of attached devices. So the question is, can you build a system that talks to IPv4 as well as IPv6? Yes. Should you? Perhaps. Is it important? Depends upon your application. But meanwhile, there is an approach, as you may be aware, from the National Science Foundation, in asking the question, is it time to think out of the box, take a clean slate approach to understanding new approaches to building or modifying or improving the internet? And right now there has been a call for research projects, basically the Future Internet Design Project, FIND, to try to bring together some wild ideas, some long-range, high-risk, high-payoff ideas.
Something like an IPvX.
Well, who knows what it's going to be.
Right.
I don't want to prejudice by even suggesting what the form will be. And it may not be a single form, but improvements that can be added to the internet, replace certain parts of it perhaps. You know, the whole way in which the internet grows is by a pipeline of ideas. The pipeline begins with research networks, where you can do anything you want in your laboratory. It doesn't have to stay up. It can be wild, it can break, but it may be as innovative. When such an idea emerges as being more useful, it goes into the prototype stage, where now you deploy it in a larger community, again with no guarantee that it's going to work or stay up, but supporting some set of applications, a little more stable. Finally, when one of those prototypes proves itself, it emerges as a production network, which is what the current internet is today. This pipeline must be kept full so new ideas can be tried, tested, and finally deployed.
And of course, that network, that human network and information network, relies on the internet to carry it to the individual practitioners. Did you envision that much of a capability being created out of your LO message in 1969?
Well, let's go back to 2 months before the internet was deployed. In September '69, the first internet node came at UCLA. In October, the first message. In July, UCLA put out a press release. And in that press release, I'm quoted as saying that the internet will be everywhere, always on, always available. Anybody with any device can connect from any location at any time, and it will be invisible. The one thing I missed was that my 98-year-old mother would be on the internet today. So what I missed was the social impact, the pervasiveness, the real depth to which this thing would go. And in fact, that's the part that almost nobody predicted at the time.
Talk about what the world would be like without the internet for a day or permanently.
It's hard to go back. It's hard to think of a time when you can't get information immediately, when you can't send a message immediately, when you can't reach out and touch someone or some device. It would slow down considerably. In fact, I suspect that many of the people in business, in science, in government today would be essentially paralyzed in carrying out their daily job functions. Imagine what the accountants would do without spreadsheets around.
To cite another a film, it would be The Day the Earth Stood Still, perhaps.
Or perhaps the day that the Mexicans didn't come to work. That movie was exactly the same effect. It's the infrastructure on which we depend, and an infrastructure which we shouldn't have to see in many ways, the internet in particular.
All right. We got about a minute and a half. Talk about your own current work, what kind of exciting projects you're overseeing, and what kind of research you're doing yourself.
Well, the kinds of work I'm interested in is varied. One area I'm very excited about is peer-to-peer networks. This is a rather interesting development in the internet where files, services, and applications are shared among a number of peers and exchanged at a very, very distributed fashion. We're studying how these systems behave, how it should be properly deployed, etc. Another thing I'm looking at is intelligent software agents in the internet, devices and structures that can achieve goals for you without you specifying how they achieve them.
We heard a lot about that 10 years ago. What happened to those intelligent agents?
Well,
where have they been?
Some of them have disappeared in the sense that they're there and you can't see them.
Right.
Data mining is an example. Automatically focusing the camera that we're looking at right now is an example of intelligence.
So they are there, but they're invisible.
They're invisible. There's a lot more work that needs to be done.
Okay. If we do another interview in 9 years or so, what do you think we'll be talking about then? You got 20 seconds.
We'll be talking about pervasive devices everywhere in our environment. We'll be talking about a global information nervous system.
And you're looking forward to that, I assume.
I am, certainly.
Good. Well, so am I. Thanks very much for talking to us today about the internet that you helped create with the idea of packet switching.
My pleasure, Marc.